Hello, calculus students, and welcome to another online lesson. Today we'll be taking a break from derivatives and talking about equations of horizontal and vertical asymptotes. The reason we need to cover this is as we get looking at more and more complicated functions to do both the derivative of and eventually the antiderivative of, we need to understand the characteristics which can include horizontal and vertical asymptotes. So as we should know, a vertical asymptote is a line which our graph approaches. The graph itself is not the asymptote, but the asymptote is a characteristic of the graph of the function. The functions we're going to be looking at today are going to be in the form of f of x equals g of x over h of x. So basically two functions being divided, which we're referring to here as g of x and h of x. And those together form a new function, f of x. Sort of like what you might use the quotient rule for. Again, two things being divided. So we can find a vertical asymptote by taking h of x, which again is this denominator here, h of x. So taking our denominator and setting it equal to 0. As we know, we cannot divide by 0, so whatever value would make our denominator 0 is something that we can approach, but we cannot actually ever have the next value of that. And that's what makes a vertical asymptote, at least in this case. So we've got a vertical asymptote is a line. Most lines we start off with as y equals, but vertical asymptotes, we don't have a y equals like a slope-intercept form because there is no y-intercept. So we make a vertical equation of a vertical asymptote always starts off as x equals, and then some constant if it's truly vertical. For a horizontal asymptote, we get to look at the function as a whole, the entire f of x, and we take x values that approach infinity, or the absolute value of x values that approach infinity. So we're basically just making our x values very large and seeing what happens to our function as our x's get bigger by a lot. So let's take a look at some actual problems. All right, so we're going to find the equation of the vertical and horizontal asymptotes for each of the following functions. As you'll notice, they're all sort of these reciprocal functions or functions where it's got a g of x divided by an h of x, a numerator and a denominator. So for the first one, to find our vertical asymptote, all we do is we take our denominator, 3x minus 2, and we set it equal to 0. We're just trying to find out when is our denominator equal to 0 because we can't divide by 0, and that will be our asymptote. We add 2 to both sides, so we have 3x equals 2, divide by 3, and we get x equals 2/3. That is the equation, the whole thing. It's got the x equal for a vertical line. It's got our constant, which is 2/3. If I were to graph this on a x and y plane here, I often will use dotted lines to show asymptotes. And so, sorry, my scale's a little bad there, but we've got 2/3, so a little bit less than 1. So something like, whoops, that was a little too far. Let's do this whole axis again. That's a little better. All right, and so then my asymptote would be at 2/3, so this would be about 1/3, and there's 2/3. So something along those lines would be my asymptote for my vertical line. Now let's talk about finding the horizontal asymptote. For the horizontal asymptote, we want x values to get very, very large. Now let's think for a second if our x values were small, like 1. If I had, let's think of our numerator as being money. And 4 times an x value of 1 gives me 4 plus 5. Let's say I had $4. And then someone gave me 5, or we added 5 to that. In relation, 5 is huge. Like, it's making a huge difference because I only had 4 to start with. I'm more than doubling my money by adding 5, and it's a really big deal. Same thing with the 3. Again, let's put a 1 in for x here. So 3 times 1 is 3. So when x is relatively small, like 1, and then I take away this 2, well, taking away 2 from $3 is a big deal. Again, I only had 3. If you take away 2, that's more than half my money, and it's a huge effect. Now let's try putting in a slightly larger x value. And by slightly, I mean a whole lot larger. Let's put in, say, an x value of 1 billion. So I would have 4 times 1 billion, which would be 3 zeros is 1,000. 3 more gets me up to 1 million. 3 more gets me up to 1 billion. So I'd have 4 billion. And then I add 5 to that. Is the 5 a big deal anymore? Or like, let's say I had 4 billion marbles in a room, and then someone added 5 more. And somebody said, hey, how many marbles you got in there? I'd say, oh, about 4 billion. The 5 is so insignificant. It really doesn't matter as x is getting larger and larger. The 4 matters, but the 5 does not. Now let's divide that. We're dividing it by 3 times a large number. And again, I'll use that same large number of 1 billion. So I have 3 billion minus 2. Again, if I've got 3 billion marbles in a room, and somebody takes away 2 of them, am I going to notice? Is it going to be anything significant? No, I'd say I still have about 3 billion marbles in there. And so what happens here? The 5 and the 2 are inconsequential. And then all these zeros here can essentially cancel out. And what am I left with? I'm left with 4/3. So as this function gets larger and larger, this 5 here and this -2 here matter very little. And I basically have a ratio of 4:3. And so my horizontal asymptote, which will always be a y equals, is just 4/3. So 4/3, that's 1/3 more than 1. So I go up to about here. And again, I can sketch sort of a dotted line to represent the asymptote. It's not actually, again, part of my graph of f of x, but I need it. Now, I can sort of sketch what the rest of this graph is going to look like. I know my graph is going to approach those green dotted lines, those asymptotes. As long as this is a positive function, meaning no coefficients are negative, I'm always in the first quadrant as part of my graph. And so approaching the asymptote, something along those lines. And then we sort of reflect it over where the asymptotes intersect, and it would be something like this. That's basically what this function would look like. I might have my stretch or scale off just a little bit, but that's the idea. I put these functions into a calculator so we can take a quick look at what they might look like. So this first one, let me turn it on. And I've just got a standard window here for my scale. And you can see that we have some asymptotes and a sketch of a graph that looks very similar to what I just drew. On the calculator, you'll notice a vertical line right around the 2/3. This vertical line right here is not actually showing up on the calculator. It's just sort of a glitch in the calculator. It just wants to connect everything, so it's making this vertical line that we can actually see. It does not do that for the horizontal asymptote, however, which we can see looks like it is about 1 1/3. Let's do the next one, and we're going to do this one much faster. So let's start with the denominator for our vertical asymptote. We have x cubed plus 8 equals 0. We want to know when the denominator equals 0. I subtract 8 from both sides. And so I get x cubed equals -8. Now to get rid of a cube, we can cube root, or we can take everything to the 1/3 power. I imagine many of us could actually sort of do a little mental work or guess and check here to figure this out. But what number, or I could take 3 of them multiplied together, or what base where I can take 3 of them multiplied together will give me a -8. Well, it's an odd exponent. I know it has to be negative, so -2 times -2 times -2 gives me -8. So x equals -2. And again, we can check that. If we plug it back in here, we end up with a -8. -8 plus 8 gives me 0, and that's where my graph would be undefined, so I have an asymptote there. So my vertical asymptote, again, x equals -2. My horizontal asymptote. Now, as we start making things very big, this -4 will be inconsequential, this 8 will be inconsequential, but let's say I put even something as small as 1,000 in there. I would have 2,000 in the numerator, but in the denominator, I would have 1,000 times 1,000 times 1,000, because it'd be 1,000 cubed. And so the denominator is growing so much faster. Eventually, the denominator will be so large that any numbers in the numerator will become inconsequential. And you'll just notice it has a higher order, or it's a higher power. And so if there's a higher power in the denominator, we are going to approach nothing. And what I mean by that is, again, let me plug in 2,000. So I have, or 1,000. So 2 times x gives me 1,000. I've already said the -4 is inconsequential. The denominator, I'm going to have 1,000 cubed, which is 1,000 and another 1,000 and another 1,000, and so that ends up being 1 billion. Well, even if I cancel out the zeros here, oops, I still end up with 2 over a billion. If you put that into a calculator, you're going to have like, I'm sorry, 2 over a million. You're going to have 0.000000002 or something like that. And as x gets even larger, the numerator is going to become even smaller in relation to the denominator. So what number are we approaching? We're getting smaller and smaller, not in the negative direction, but just towards 0. So my my horizontal asymptote is going to be y equals 0. And again, it's because there's a higher order in the denominator. Number 3, if I set x squared minus 1 equals 0, add 1 to both sides, I get x squared equals 1. I square root both sides. I ask myself, who wrote that square root? I, of course, did. And so I have 2 answers, positive and negative 1. So there are actually 2 vertical asymptotes, one at x equals 1 and one at x equals negative 1. Now for my horizontal asymptote, y equals, you'll notice there's no x's up in the numerator. So as my denominator gets larger, as I put in larger and larger values for x, like even 1,000 squared, I'll end up having a million minus 1 in the denominator. The minus 1's inconsequential, so I'd have 3 over a million, which is very tiny, approaching 0. As x gets even larger still, it'll be closer and closer to 0. So that's what we're approaching. So our horizontal asymptote is y equals 0. Working sort of backwards on number 4, once again, you can see it has a much higher order in the denominator. There's no variable in the numerator. So we're going to have a horizontal asymptote at y equals 0 for number 4. Number 2, 3, and 4 all have a higher order or a higher power of x in the denominator, and that's why all of those become 0 essentially as x gets very large. And so we have a horizontal asymptote at y equals 0. Now, for our vertical asymptote for number 4, let's set it equal to 0. We have x squared plus 2 equals 0. Subtract 2 from both sides. So now I get x squared equals negative 2. Square root both sides, and I've got a problem. I cannot square a negative. So there would be no solution here to this problem. Well, no solution means there is no asymptote, because there's no way to make this denominator equal 0. So the only asymptote number 4 has is a horizontal asymptote at y equals 0. So hopefully this review helped a little bit. We can talk a little bit more about this next class, but we will be having a test the class after next, so 2 classes from now, on our applications of derivatives. Until next time.